All right.
Okay, hey everybody. Thanks for coming out to our session. My name is Kevin Moore, and this is my colleague Michael. We are both data scientists on the Einstein modeling team, and we'd like to show you a bit about some of the behind-the-scenes stuff that we've developed to help automate the training and deployment of machine learning models across a wide variety of use cases here at Salesforce. So, of course, don't buy any stock based on the stuff that I'm telling you right now. You've seen these a million times now, I bet. So the first thing I want to do is have the internet trying to connect. OK, I think we're good. OK, great. So the first point I want to make is that developing real-life machine learning models is a really time-consuming and person-intensive task. It takes lots of data scientists to do the work that goes into building these models. So for example, you usually have to start out with an ETL phase where you bring all the data that you want to use to create your models together in one location. You might have to join multiple tables together, do some deduping, do data validation processes. These are all very time-consuming and require people usually to do these. Once you have your data in one location, then you need to do feature engineering steps, which is converting all of the fields that you have in your Salesforce or whatever data you're trying to build the model with into numeric vectors that you can use to train machine learning models. Once you have those, then you need to train a bunch of machine learning models and pick the best one. So depending on your data source or your use case, there's a wide variety of machine learning algorithms out there, and there's a wide variety of settings for each one of those machine learning algorithms. Not one algorithm is going to be the best fit for all of the problems. And so if you're trying to build a lot of different machine learning use cases, you're going to need to try a lot of different models because some of them will perform better for certain customers, some of them will perform better for others. So there's a model training and evaluation phase where you split the data into training data and test data, and then repeatedly train and test models and pick the very best ones to deploy for that specific use case. After that, you need to deploy the model so it can actually do real-time scoring and process incoming data. And then finally, you want to have the ability to retrain the model when you need to, when new data is coming in, so that your model stays relevant and useful for whatever use case you're doing. So now imagine that's a very time-consuming task that takes usually a team of data scientists a few months to do. Now imagine multiplying that by all the use cases that Salesforce has. So use cases across Sales Cloud, Service Cloud, Marketing Cloud. It would just take all the data scientists it would take more data scientists than exists to do this. And so we really need to leverage automation in order to do a lot of these repetitive tasks, or at least help current data scientists develop code and iterate faster. So one of the things I want to point out is that designing machine learning algorithm or designing machine learning models also has additional complications above traditional software engineering. There's other types of bugs you have to worry about. So to kind of orient you, in normal software engineering, you have to worry about, is the algorithm that you are applying the correct algorithm for the problem? Is it solving the problem that you want to solve? And did you implement it correctly? There's a whole bunch of ways to get both of these wrong, but if you get them both right, then you're solving the right problem in the right way, and your code is happy. It's doing what you want it to do. When you start dealing with messy real-world data and models, you start introducing other dimensions that you can have fail. So for example, now you still have the algorithm and implementation correctness sides on the bottom, but you also have this extra dimension of issues that you can have with your model. So now you start having to worry about, well, is my model overfit? Is it basically performing very well on training data, but not generalizing well to data it hasn't seen? Is it a useful model to actually use in practice or not? In addition, there's issues with the data itself, even without training any models. Does your data is it big enough? Does it have enough correctly identified labels? Is the data balanced correctly? Are there enough examples of positive and negative cases if you're doing a classification problem? Do you even have features in your data that are predictive of what you're trying to predict? These are all things that are additional difficulties on top of normal software development, but these are also things that can be automated. These are things that are easy to check if you can develop a systemized way of checking these things. So what have we done here at Salesforce? We've developed a machine learning library on top of Spark We've chosen to use Spark because of a lot of useful information, like right here. So Spark is basically a general-purpose distributed computing engine. So it's great for processing big data in all sorts of different applications. It's open source, so it's got a great community of contributors that are always adding new features and algorithms to it. And especially in the machine learning setting, it's got a lot of the right kind of abstractions for our use case. They have this notion of transformers, estimators, machine learning pipelines that makes it a very extensible framework for building arbitrary machine learning pipelines. And it's very useful for us at Salesforce because we have a lot of different machine learning use cases. And so we want to be able to leverage all this awesome stuff, so we're working on top of Apache Spark. And so specifically with Salesforce, we have a lot of structured data. We've got very rich schemas, as I'm sure you're all aware of. We know the relationships between different objects. We know the field types. There's lots of metadata that we can leverage, and that's really what helps us do some of the secret sauce that we do, is knowing all that metadata information. We have lots of different internal teams developing different machine learning applications across different clouds. And we also have a lot of developers that don't have a lot of SparkML or Scala experience, so we want to develop a framework that helps simplify actually writing the code. So in addition to automation, we want to make it easy for the developers to actually do the data science that they're here to do. So we've built a simple declarative type-safe syntax to do all this stuff. We have a lot of reusability and extensibility. So these same algorithms are used across all the clouds where we have machine learning apps on Salesforce. Everyone's using this, or there's tons of people using this unified machine learning framework. So I want to point out a few things under the hood and then hand it off to Michael, who will show a cool demo of how this actually works in practice. So I want to talk about how you do automated feature engineering, feature selection, and model selection, because these are really the core things that we're trying to solve when building a machine learning framework. So automatic feature generation is basically taking the columns, the data types that you have in Salesforce, which we know the types of. So these might be things like email addresses, text fields, pick lists, numeric features of all sorts, phone numbers, and turn these into feature vectors that you can then use to train machine learning algorithms. So some of these features, it's relatively straightforward. Others, it's a more time-consuming process. But because we know the type, we can do special things to these special fields. So for example, with email addresses, we can do email-like transformations to them. We can check, is this a spammy email address? We can look it up in a database, do spam scoring on it. We can look at the email domain, pivot out the domains, and keep track of the top 10 ones. For phone numbers, we can check the country code, get geolocation information from that. We can check, is this a valid phone number or not? For numeric features like ages, we can automatically bucketize these into different demographic groups, for example. For subjects like text, like big text boxes, we can pick out the top terms. We can also do automatic language detection, which is extremely important for the work that we do, because we're dealing with customers all over the world. And so detecting the language and applying specific text processing pipelines to those specific languages is crucial in order to get actual models that work across a worldwide customer base. And things like zip code, you can leverage external data like average income or weather or population, pull those all into a single feature vector, and then start training your machine learning model. This is all done behind the scenes. These are just a kind of an example of the transformations that go on back there. How do we select the best features? We calculate tons of descriptive statistics, so things like mean, min, max, variance, how often this field is empty. We ensure that these features have acceptable ranges. Are they not all null, for example? Do they have a variance that's bigger than 0? We ensure that these are valid features. We check if they're leakers. What we mean by that is sometimes you have fields that are filled out after the field that you're looking to predict is filled out. Those fields aren't available when you're scoring, so that's not actually useful to include in your model. So those are things we check for. We check if there are features that are too highly correlated with the feature that you're trying to predict. Those won't be super useful in building models. We check, do the features help the models? Are each individual features making our models better? Are they predictive of what we're trying to predict? And finally, we have automatic model selection, which is basically training a whole bunch of models and then picking the best one from that mix. So you can imagine this as there being a cost or an objective function that you want to maximize, and you want to get that point in the upper right location where that's where this model is performing the best, and so you want to try a bunch of different hyperparameters. So these are things like maybe the number of trees in a random forest, regularization parameters in logistic or linear regression. And there's a whole bunch of intelligent ways to search through this space and find that that's the best point to use for your machine learning model. So you can do grid searches, random searches, bandit methods. But the point is we have a competition between all the different models to pick the very best one for all the different use cases. So now I will hand it off to Michael, who will do a little demo.
Thank you, Kevin. So
Wow,
I'm going to do a quick demo of our AutoML capabilities on a very classic toy data set, which is the Titanic data set. I'm pretty sure some of you know this data set. It's from the machine learning competition website Kaggle, and usually when people want to start machine learning competition, they will do this first one for training and for fun. So what's the story behind this data set? So we have data about passengers at the Titanic. We have information about them, for instance, their name here, gender, age, the class, if they were in first class, second class, third class. Here, we have this is the number of sibling and spouse they had, number of parent and children, the information about the ticket somehow, the price of the ticket, the cabin and where they embarked. And the goal here is to train this data in order to predict whether they survive or not. So it's a binary classification problem here. As you can see here, the data is pretty interesting because we have either numeric features here and also text features like the name, and also categoricals. That mean the features that contain only a finite set of values. For instance, we have the gender here and the embark, which is a categorical features. And also, as you can see here, unfortunately, the data is not totally complete. There's some missing values, for instance, here. And for the cabin, there are lots of information missing. So what we're going to do is, so we have Wi-Fi issues, but what I did just before the talk, I created quickly a predictive app that is using our framework and going to try to train the Titanic data set. So I can show you the results of this training. So it only took 20 seconds. And I don't want to go all over the logs and so on, but basically what it did, it took the raw features, as you just saw, it do all the process of feature engineering, automated feature selection, and model selection automatically. And I just want to show you the last part, which is model selection. So the logs here is showing you the different models it tried. So for instance, these 4 pieces is basically DTC, that means the decision tree algorithm it tried, with the different set of hyperparameters. The second one is the logistic regression. And he tried also a third algorithm, which is random forest, okay? And as you can see here, it said that the best algorithm was the random forest, actually. And just below, there are metrics about the training that are here. So I don't want to go over it pretty much because it's very data science. But you can see here the error, which is basically the misclassification error rate, and we have 15% of error rate at training. And we tried also to evaluate that on the test set, and we have some error of 26%, which is pretty decent. So it's pretty cool. So back to the we have some Wi-Fi issues, so let's try to connect. Let's try that. OK, let's try the Dreamforce 7.
Oh, yeah.
Great, awesome. Okay, so that was the demo, and I'm going to show you the interesting part of this predictive app I wrote, and this is the part that does like the automated feature engineering, the automated feature section, the automated model section. As you can see, all these processes are only done thanks to 1, 2, 3, 4 lines, which is pretty impressive. And to show you how impressive it is, let's compare to a code a regular data scientist will write on Spark in order to achieve the same thing. So let's pretend we're all data scientists and we know Spark. So to train this model on the Titanic Data, what we'll need to do is first try to replace all the missing values we saw in data. So we saw that the field, the age, had some missing values. So we decided here to replace this missing value by the average. Same thing by the field embark. We decided to replace by the value s because it was the most frequent. So this is the first step. So we have to implement some code here. But it's not over. So here we need to transform all the categorical features into numeric features in order to be prepared for training. So this is what this piece of code is doing. Then we concatenate all these features into a vector. And we're instantiate the logistic regression. We're adding some grid of hyperparameters for grid search. We're doing cross-validation of basically it's machine learning, data science. So you see tons of code. And this is only for trying to train only on the logistic regression. So to do that on random forest decision tree, we have to write much more code also. So all the code I'm showing you right now, it is now done with only 4 lines of code, which is pretty great. So that was the case of the Titanic data set. But now in the context of Salesforce, we're working on with very different customers, having different problems and lots of different data. So basically, all this iterative, repetitive process we need to do, which is very time-consuming, we're automating thanks to this framework. So right now, what we can do now is we can now stop reinventing the wheel, and because we're now standardizing all this iterative process in order to make this AutoML more reusable and more modular. So as a result, instead of spending months of writing this model in order to train different data and so on, with our AutoML framework, it only takes hours. And it is now used in Salesforce right now. So as a result, this system of automation is used, and Salesforce with this system is predicting about 500 million of predictions per day. And we're deploying lots and lots of models here for Service Cloud, Sales Cloud, Marketing Cloud. So there's no y-axis here because PR at Salesforce asks us to remove this axis. But believe me, the values are pretty high here. They're pretty big values. So here we're making more and more models, which are AutoML models. They're not mechanical Turks. That means that behind each model, there is no personal data scientist who spent time looking at the data and manually did the feature engineering and manually pick the best model and so on. So because honestly at Salesforce, I don't think we have enough data scientists that will build all these models. So as a quick recap, machine learning is hard. As Kevin mentioned at the beginning of the talk, it's adding this third dimensionality, which is for us an extra layer of complexity. And what we want to do is to minimize the impact of this complexity by making this process used to be time-consuming, automatic, and more easy to use and to reuse again and again. And as a result, also, we achieve models that are almost as good as models that would have been made by real data scientists by spending times, I don't know, maybe days or weeks on the data and so on. And we do that with only the 10% of time. So that's it. Thank you.
Yeah. So I think we're out of time. We'll be happy to answer questions out there on the floor if anyone has any questions. But yeah, thanks everyone for coming.